In this video, I'm going to show you how to integrate some more complicated integrals by a method called integration by parts. Now, recall the product rule for differentiation. So if I want to take the derivative of u times v with respect to x, this would be u times dv dx plus v times du dx. Now, I'm going to work backwards and I'm going to integrate both sides with respect to x. So we have the integral of d dx, u times v, equals the integral of u dv dx with respect to x, plus the integral of v du dx, also with respect to x. So you can see that on the left side here, the d dx's cancel off. So I have the integral of u v, and I have the d equals the integral of u dv plus the integral of v du. Now, since I'm taking the integral of the derivative of uv, they're inverses of each other, so we just get u times v equals to the integral of u dv plus the integral of v du. Now, what we're trying to integrate is actually the integral of u dv. So I'm going to isolate that, and I'm going to move the integral of v du to the other side. So I have the integral of u dv is equal to u times v minus the integral of v du. And this, kind of a little formula here, will help you to integrate by parts. And I'm going to show you how this works. The integral on the left corresponds to the integral that you're trying to do. And then the parts replaces it with some stuff, which is u times v, and another integral, which is v du. Now you'll make progress if the new integral is easier to do than the old one, which is what your goal is. So let's take a look at a couple of examples. So this first one here, we have x times e to the x dx. Now, if you recall, we can't integrate each part separately. There's no such anti or reverse product rule. So we're going to use integration by parts here. We're going to let u equal to x, and then the dv will equal to the e to the x times dx. So we're splitting these two up like this. Okay, so I'm going to take the derivative of u, which is dx, and then we're going to integrate dv. So v is equal to e to the x. Now, we don't need to worry about the c, the constant, because in the end, it's going to cancel off. So you don't have to put that in right here when we're integrating. So according to our formula from before, so the integral of u dv, which is what we're trying to integrate, is equal to u times v, which is these two expressions here. So it's going to be x times e to the x. And then minus, and we have the integral of v times du. So v is e to the x. Oh, sorry, e to the v times u, e to the x here. And then du is dx. All right, so this is now something easy that we can integrate. So we have x times e to the x, and the integral of e to the x is e to the x. And then now we put the plus c. Let's take a look at another one. So here we have the integral of 4 times x times sine x dx. So we're going to let u, and it's your choice. So if one way doesn't work very well, you need to kind of switch your u and your dv. So I'm just going to guess and say that, let's say that u is equal to 4 times x, and dv is then equal to sine x times dx. So we have du, we're going to take the derivative, is equal to 4 dx. The integral of dv is v, and the integral of sine x is negative cos x. So we have u times v as part of our formula. So we have negative 4x times cos x minus the integral of v, which is negative cos x. So this will become positive cos x times du, in this case, which is 4 dx. Now notice that once we've done this, your integral only involves x here still, okay? And this time we can see that the integral of cos x is much easier to integrate than having the two x's over here. So we have negative 4x cos x, and then the integral of 4 cos x is 4 times sine x, and then plus c. All right, let's take a look at another example. Now, in this example, and in some examples, we need to do integration by parts 2 or maybe even more times. So let's say we're integrating ln or natural log of x all squared. So we're going to let u equal to the natural log of x squared. And dv then simply, because we don't have anything else, will equal dx. So the derivative of u is du, derivative of natural log squared will be 2 times the natural log of x. And the derivative of natural log of x is 1 over x. So 1 over x. And this will be dx. The integral of v, dv, is v. Integral of dx is x. So the formula is u times v. So it'll be x times the natural log of x squared minus the integral of v, which is in this case x, times, and then we have 2 times the natural log of x divided by x dx. Now the nice thing is that the x's cancel off. So we have x natural log of x squared minus the integral, or 2 times the integral of the natural log of x dx. So we don't know an integral for the natural log of x, but I'm going to show you we're going to have to integrate by parts again. So we're going to let a new u equal to the natural log of x, and then dv equals dx. So the derivative of u is equal to 1 over x dx. Integral of dv is v equal to x again. So in this step here, we're going to say x natural log of x squared, which is from before. Now we have a 2 here, okay? And we're going to multiply that by the integral of the natural log of x, which we had to do integration by parts again. So this will be x times ln x, or the natural log of x, minus the integral of x times 1 over x dx. And this is fantastic because we can see that this is much easier to integrate since this is all going to become 1. So we have x times the natural log of x squared minus 2x times the natural log of x, and then negative 2 times the negative here will become plus 2, and the integral of 1 will just be x, and this will be plus c. So you can see in this question, we had to integrate twice, or use integration by parts twice, before we were able to integrate all the way. Now I'm going to show you one more type of problem. Now in this example, we do have to do integration by parts twice, and you'll see why. And then we actually have to do something else that's a little bit special, which is to solve for the unknown integral. And I'll show you what that means. So we're going to integrate e to the x times sine x dx. So we're going to let u equal e to the x. And then dv equal to sine x dx. So the derivative is e to the x dx. The integral is v is equal to negative cos x. All right, so we have u times v. So this will be negative e to the x times cos x minus the integral of negative cos x, so it's going to be positive, times e to the x dx. All right, this doesn't seem very helpful, so let's try this one more time. So let u equal e to the x. So we're now integrating the second integral by parts again. So dv is equal to cos x dx. And derivative of u is e to the x dx. And integral of dv is v equal to sine x. All right, so we have negative e to the x times cos x plus, and then we have now u times v, so e to the x times sine x minus the integral of sine x times e to the x dx. So actually I'm going to place my e to the x first. All right, so I'm not sure if you've noticed, but this integral right here is actually what we started off over here. So let's call that I for integral, okay? So if I did that, I would have negative e to the x cos x plus e to the x sine x minus I, since I'm saying that that integral is called I, and then we have the plus c for the constant. So knowing that this is I can say that all of these are equal to the integral. Okay, so the integral is equal to I, and I is this integral. So notice now I have two i's. I'm going to move the second I to the left. So we have 2i is equal to negative e to the x times cos x plus e to the x sine x plus c. And to get the I, which is actually the integral on its own, we need to divide all the terms by 2. So now I have I is equal to negative a half e to the x times cos x plus half e to the x sine x. Now I don't have to half my c because c is a constant number and it can be anything already. So halving c is just like still another new constant. So we can leave it as plus c. So in this case, we had to integrate twice, which still didn't help us. And you can see that it's very circular because we end up with the same thing. And when that happens, you should know that this new integral that you have is actually the same as the original. And we're going to set it equal to I. And then we could actually then isolate I, which will then be the integral.